Good day, ECO235 students. This is the content for week 6. You are going to be dealing with returns to scale, and we could have started with constraint optimization and particularly dealing with production equilibrium. However, you have not done this in ECO231. In ECO231, you've only started chapter 6. Whereas in order to work through the problems dealing with production equilibrium, you would need to have completed chapter 7 as well. So this week's notes will be fairly short as we'll only keep our focus to returns to scale and only introduce the topic on constraint optimization relating to production equilibrium. The prescribed readings for this week is chapter 8.3 of your prescribed textbook. This week in ECO 231, you were told to shift your focus now to the supply side. Now you're looking at producers, and chapter 6 introduced you to production. So now in ECO 235, we will do applications of what you are going to be learning pertaining to chapter 6 and 7, and that is going to relate to production equilibrium. So just to recap, you were taught that a production function, it shows the highest output Q that a firm can produce for every specified combination of inputs. Now the two inputs that you would focus on or that we use in our analysis is namely labor with the notation L and capital K. And here we are given the form of your production function. Your output Q is equal to a function of capital and labor. Now we're going to keep our analysis to just that and just remind yourself constantly that your production function relates your quantity of output Q, so it relates your output to the quantities of the inputs, and these two are your inputs. So as you will go on in microeconomics 231, you will go on to learn about the budget constraint or the cost constraint that the firm faces. We will then move on to production equilibrium. So later on, we will apply this knowledge in ECO 235. So you will learn that producers ultimately want to maximize their output, but they are faced with cost constraints. So this is going to imply that producers also need to consider how they can minimize costs. But this we won't deal with this week as you haven't dealt with it in ECO 235 yet. Sorry, 231 yet. We will come back to this when we return in week 7. So this week we're just going to focus on returns to scale. Now, this is called a Cobb-Douglas function. And a Cobb-Douglas function, this function over here, is a very specific type of function. It comes in this particular form. So please note that this particular form represents your Cobb-Douglas production function. So here you have Q. Q is of course going to represent output. And then C, this constant over here, that alpha and beta, which are these exponents, all three of these are positive constants. And then you have L, which is going to represent labor, units of labor, or how much labor, and K is going to represent how much capital. So this is the form of your Cobb-Douglas function, and we are going to use it to see returns to scale. So another assumption we are going to make is that alpha and beta are less than 1, but they are positive. Now, Cobb-Douglas functions are used quite frequently in economics, and it can be used to model production. We can also see it being used to account for changes in technology as well as productivity through changes in C. So the bigger this C becomes, this constant, the more output can be produced for a given amount of our inputs, labor and capital. Okay, so your COP Douglas function, just to recap, it's going to represent the relationship between your two inputs, and we are focusing on labor and capital, and the number of outputs that can be produced. So how are you going to have to do applications regarding this and returns to scale? So in ECO231, you learnt about returns to scale, you learnt about constant returns, increasing returns, and decreasing returns to scale. Now we can use the Cobb-Douglas function to determine if we have increasing, decreasing, or constant returns to scale. So for your general Cobb-Douglas production function, if you sum your exponents, these exponents, alpha and beta, and it's going to help you indicate what the returns to scale are. So firstly, if alpha and beta are equal to 1, it's going to indicate that you have constant returns to scale. So what does it mean? You know what constant returns to scale are. It means that there is a proportionate change in output as the inputs change in the same proportion. So if we were to double our inputs, outputs would also double. So the proportionate change in output is the same as the proportionate change in the inputs, and that is your constant returns to scale. And hence, these two, if you were to add them, it would equal to 1. The next is we can look at decreasing returns to scale. Now, you know that with decreasing returns to scale, if there is a doubling of your inputs, your output is going to less than double. So in this instance, if we were to sum those exponents, alpha and beta, you're going to find that they are less than 1. And that is going to indicate to you for the Cobb-Douglas function that you are dealing with decreasing returns to scale. So the proportionate change in output is less than the proportionate change in input. Lastly, we have increasing returns to scale. So here you can see the sum of alpha and beta is greater than 1. So the proportionate change in output is greater than the proportionate change in the input. And that's going to tell you you have increasing returns to scale. So remember, if you were to double labor and capital, if output more than doubles, you're dealing with increasing returns to scale. So let's look at an example. Here you're given your Cobb-Douglas production functions, and you've got two notes. These are all positive, right? And here you've got your constant and your exponents alpha and beta. Here you've got 0 0.4 and 0 0.6, and you've got 0 0.5 and 0 0.6. Now just going on what we learned, if I add those two, it's going to equal 1. So I can immediately say that this function is going to give me constant returns to scale. Whereas if I add these exponents, I'm going to get 0 0.5 plus 0 0.6. That's my alpha plus beta. And that's going to give me 1.1. So now I know that I'm going to be dealing with increasing returns to scale. But let's test this. So it says calculate the level of output when L is equal to 10 and K is equal to 15. So for each of these two functions, you're going to substitute L is equal to 10 and K is equal to 15 for each of these, and you're going to determine the level of output, and the level of output pertains to Q, right? Then the second question says calculate the level of output, right? So calculate Q again when both inputs are doubled. So if I'm going to double my inputs, if L doubles, it's going to double from 10 to 20, and if K doubles, it's going to double to 30. So therefore you determine what output is if L is now 20 and K is 30, right? Now we need to comment on the returns to scale, because between question 1 and 2, we've doubled our inputs, but what happened in terms of output? Did Q also double? So let's have a look for the first example, right? Here your Q is equal to 50L to the power of 0.4 times K to the power of 0.6. So if I substitute, initially we had 10 for labor and 15 was your capital. So if we substitute those values, we get 637.71. That is our output Q. Now, when you double your inputs, if you're going to double both inputs and it doubles to 20 and 30 respectively for labor and capital, you can see that your new value for your output is 1275.42. And if you check, if you were to double this and you say 637 times 2, which is a doubling of that, it is in fact equal to that value over there. So you can see that when you doubled your inputs, right, our output also exactly doubled. And hence we can see that we have constant returns to scale because we doubled our inputs and outputs also doubled. Let's look at the following example. Now remember, if you were to look at these exponents alpha and beta and you were to add them, we would immediately see that we're dealing with increasing returns to scale. But let's test that. So if we first calculate what our output Q is equal to when labor was 10 and our capital units were 15, you got your output equal to 802.83. Now we double our inputs. We doubled our inputs. What happens to output? Does output double or does it more than double? So now you can see after we've doubled our inputs, output is now 1720. Now, very quickly, if you were to double 802, you're going to get 600 and sorry, if you were to double this, you're going to get 1604 roughly. So you can see by doubling this, it is in fact smaller than that value. So therefore, we have increasing returns to scale because although we doubled our inputs, our output has more than doubled. So you can see that this is greater than a doubling of this value. So here are two homework exercises. Now the answers are already available on eCanva, just the final answers. So please do work through these questions and then we can discuss the answers. Now, just to introduce the final topic, we will thoroughly work through this topic when we return in week 7, when you deal with chapter 7 in microeconomics. I can then continue with this particular topic. And the prescribed reading is the same as well, right? So up until now, you've learned that you have a production function, and we've recapped what a production function is, that it relates the quantity of the output to the quantities of the inputs. It shows that highest output that a firm can produce for every specified combination of inputs. And those two inputs we had was labor and capital. And we also see that firms would like to maximize output Q, but they are subject to budget constraints. So these 2 points relate to chapter 7, right? So let's skip ahead. And then this is just a recap of what you've done in microeconomics this week, where you have your production function given in the form of Q is a function of labor and capital. So here you have a production function and it's represented as an isoquant. And your isoquant is the convex curve that is downward sloping. And you also saw that the slope of your isoquant is given by the marginal rate of technical substitution, right, of labor for capital, and that is given by the change in your capital over your change in labor. And you know that that is in fact going to be negative because it is a downward sloping curve and it's convex and it represents the diminishing returns. So your slope, the derivation of this was done in ECO231 as well, and it's given by the ratios of our marginal products, our marginal product of labor over our marginal product of capital. And in order to get this, can you guess what you need to do? Here you've got a function of two variables. Your production function is a function of labor and capital. So therefore, you're going to have to do partial differential calculus to get your marginal product of labor and marginal product of capital. And from that, you'll be able to derive the ratio of your marginal products. So I'm going to conclude here, but note for this week, you do not have to do this work. We will continue with this in week 7 when we return from the week break.